All right, students, we're on our second video. I noticed in my first video that I had spelled instantaneous incorrectly. So if you were copying down, you might want to check your spelling, instant and then A-N-E-O-U-S. So make sure you get that correct spelling, and sorry for the mix up there. All right, so we're going to move on to the next section, and I have some steps that we'll follow to determine the value of C in Rolle's theorem and the value of C in the mean value theorem. So as I go through the examples, you can refer to those steps. But I will say that the two steps where you need to verify, I am requiring that you show this because I want you to know that those conditions have to be held in order for the Rolle's theorem to apply. And then likewise, for the mean value theorem, I want you to make the statement about continuity and differentiability. So make sure that you do have the statements verifying those conditions are held. All right, so we're going to move on to the Rolle's theorem examples. And part of what you're asked to do is to determine whether Rolle's theorem even applies. And then if it does, that you'll find all the values of C where the derivative is equal to 0. So on our first problem, and I'm going to call this a red flag problem because not only is it an absolute value, but we also have an x in the denominator. If you have an x in the denominator, then somewhere in that domain, you probably have a discontinuity. So we need to check the interval from -1 to 1, and if this function is not continuous in that interval, then Rolle's theorem doesn't apply. Well, that is the case. F is not continuous on the interval from -1 to 1 because x cannot equal 0 in that function. So anytime that you have a variable in the denominator, you should be suspicious about the continuity. And so this would be your verification, and then you would say that Rolle's theorem does not apply. So Rolle's theorem does not apply. And I know some people will abbreviate, and I don't mind if you abbreviate, just make sure that you know what you're talking about there. So on our interval from -1 to +1, the graph is not continuous, and so therefore Rolle's theorem doesn't apply. Okay, another graph that is, or type of graph that you should be suspicious of, would be any of the trig functions other than sine and cosine. If you have a trig function that has asymptotes, and all of them except sine and cosine have asymptotes, then you need to be concerned, or at least suspicious, that maybe Rolle's theorem will not apply. And that is the case with the cotangent of x over 2. You can check out that graph. And I would recommend that you do that on part A as well. But if you check out that graph on the interval from 0 to 4 pi, you have vertical asymptotes occurring And so therefore, that graph is, f is not continuous on the interval from 0 to 4 pi, and then your conclusion is that Rolle's theorem does not apply. And if the theorem does not apply, you have no other work to complete. So those first two, as I said, are what I would consider to be red flag type graphs. Anything that has an absolute value in it, which might indicate a sharp turn, or a variable in a denominator, which might indicate a lack of continuity, or a trig function that is not sine or cosine, again, a lack of continuity. Those are all types of functions where you might not have Rolle's theorem applying. Now, it would depend on what the interval is. If you narrow down the interval enough, or if it's on beyond where the discontinuity occurs, then Rolle's theorem could apply. So you have to check the interval as well as the type of function. And you could, on the trig ones, you can check that out graphically, or if you've got something algebraic, you can check that out as well. Now, for C, the theorem is going to apply, and so I'm going to clear the ink and give myself a little more space to work. So on part C, I have the cosine of 2x as my function. My interval is negative pi to positive pi. So I want to make sure that I verify. So I will make the statement that f is continuous on the interval negative pi to positive pi. And that's because it's cosine. Cosine is continuous on the whole real number system. So f is continuous. Cosine is also a smooth curve. And so f is also differentiable on, and there it didn't have to be differentiable at the endpoints. So you can just state that as an open interval there. So it's differentiable on the open interval from negative pi to positive pi. And that just means there are no sharp turns. It is a cosine graph, and that's going to be smooth turns. And then the last condition that has to be true is that f of A has to equal f of B. So negative pi is your A, positive pi is the B in this interval. So we have to check f of negative pi. All right, so that would be the cosine of 2 times negative pi, or in other words, that would be the cosine of negative 2 pi. And in going around the circle, the cosine of negative 2 pi would equal 0. Or excuse me, the cosine is your x value. That would equal 1. And so we have the cosine of negative 2 pi equaling 1. Then I can check f of pi, and I'm really struggling with space here. So I'll check f of pi. And so that's going to be the cosine of 2 times pi, or in other words, the cosine of 2 pi. Again, that's on the circle, the same place where the 0 is, and the cosine is the x value. So it is 1. So we do have the verification that f of negative pi is equal to f of positive pi. So in other words, f of A equals f of B. Now, all that I have written so far is just the verification that Rolle's theorem applies. So I'm not able to write very small with the way this goes. So I'm going to have to carry over into another area to get the rest of this. So Rolle's theorem applies, and now I'm ready to work on the condition, or I'm ready to work on what happens now that I know that Rolle's theorem does apply. So I'm kind of covering up this next problem, and I'll use this space in here to do the rest of part C. So to do the rest of part C, now that I know that Rolle's theorem does apply, I am now guaranteed that there is a place where f prime is going to be equal to 0. So now I need to find f prime of x. So f prime of x, I have cosine of 2x. So the derivative of cosine is negative sine of, and I keep my angle, 2x. And then because my angle is not just an x, then I have to do the derivative of the angle. So that would be a 2. So f prime of x is equal to negative 2 times the sine of 2x. And so there has to be a place, according to Rolle's theorem, where f prime of x is equal to 0. So I'm going to set negative 2 times the sine of 2x equal to 0. Now, I can divide both sides by negative 2 and just have the sine of 2x equals 0. So now I am looking at 2x equaling the inverse sine of 0. So I need to know, where does the sine equal 0? So at what places do I have, and I need to be in my interval. So from negative pi to positive pi, where is the y value equal to 0? Well, that would happen. So it happens at negative pi, and it happens at 0, and it happens at positive pi. So I would have 3 places here. So 2x could equal negative pi. 2x could equal 0, and 2x could equal positive pi. So actually, I have space over here that I didn't realize I had. So 2x could equal 0, 2x could equal positive pi. All right, and then when I solve, I can divide both sides by 2. I get x equals negative pi over 2. I get x equals 0, and I get x equals pi over 2. So those 3 values are places where your derivative equals 0, and those 3 values are between negative pi and positive pi. So Rolle's theorem did apply, and we found 3 places in our interval where the derivative was equal to 0. All right, so that is a demonstration of finding out that Rolle's theorem does apply, and then finding those x values where it applies. I've got a couple of other examples left. I'm going to move on to another video to wrap this up.